This screencast will cover the basics of how to name and identify alkenes and alkynes. Alkenes and alkynes just contain unsaturated hydrocarbons. Unsaturated hydrocarbons are those that have one or more double or triple bonds. So if we think about our typical alkene that had the formula CnH2n plus 2, we could look at a simple one like ethane. And ethane would have 2 hydrogens for every carbon. So there's the H2n plus 2 that are on the N carbons. So to make that unsaturated or no longer filled to capacity with hydrogen atoms, if it's no longer fully saturated with hydrogen atoms, we'd erase 2 hydrogen atoms and we'd put a double bond in there. Now, instead of H2n plus 2, we just have H2n. So our alkene is going to have H2n because we've erased those 2 hydrogens off the end of the chain in order to make it no longer saturated with hydrogens. If we look at a triple bond, let's start with ethane again and go ahead and erase 2 hydrogens. We'd be unsaturated. And we could put in a double bond, but we want a triple bond, so that means that we're going to have to erase 2 more hydrogens and replace that with a triple bond. And so now, not only have we erased the plus 2 hydrogens that a normal alkane would have, we've also taken away 2 more hydrogens. So our alkyne formula is CnH2n minus 2 because we have to subtract 4 hydrogens from an alkane to get all the way to an alkyne. So let's look a little bit more at the structure of alkenes. Their double bonds are going to have bond angles that are about 120 degrees apart. We need to split the 360 degrees into 3 equal bond angles, and they're each going to be about 120 degrees. The typical bond angle here, the C to H bond angle, is a little bit greater than 120. But if we put a larger group there, let's say we have propene, which is essentially like having a methyl group onto the alkene, that's going to take up a little more space, and it's going to widen up that bond angle to relieve a little bit of steric strain that's going to form here between the hydrogen and the methyl group. So that's going to be a bond angle of more like 125 degrees to relieve a little bit of that strain. There is not any free rotation around that carbon-carbon double bond. It's sort of stuck in place, if you will, and restricted, we call it. Since there's no rotation about this carbon-carbon double bond, our groups can end up in one of 2 places. Groups on either side of a double bond can end up being cis on the same side. And so here we see in butene, so we've got 4 carbons. We've got 1, 2, 3, 4 carbons in a row. And we've got a double bond that starts on carbon 2 and goes to carbon 3. So we're going to call it 2-butene. But for the 4 carbons, ene for the double bond, 2 is the number where the double bond starts. So the double bond starts on carbon 2, goes to carbon 3. And cis means that these 2 methyl groups are on the same side. In the trans 2-butene, the 2 methyl groups end up on opposite sides of the 4 carbon chain. And if we look at their properties, they have unique properties. The melting points are different. The boiling points are different. And what we find is that cis and trans isomers have different chemical and physical properties. And so they're unique molecules. If we look a little bit closer at 3D models of them, we find that in the cis isomers, there's more strain here, and that's steric strain, that non-bonded interaction where these atoms are at least 4 atoms away from each other, these 4 carbons in a row. And that's really the hydrogens that are even farther away that are coming too close into contact with each other. I'm going to erase that again just so that we can see that in our 3D model, these are overlapping in the cis-butene, whereas we have room in the trans isomer. And so because there is some of this steric strain, some of these groups coming too close together on the same side of the double bond, the cis is not preferred. It's actually the trans isomers that are more stable due to less steric strain, less of that overlapping of electron clouds that is not favorable. And so we'll find reactions that prefer to form the trans product. And we'll find that the trans products, the trans alkenes, are energetically favorable. So they're going to have lower energies. So let's get into naming alkenes and alkynes. Let's start with alkenes. We're going to focus first on IUPAC nomenclature, where we're going to use "ene" to show the presence of a double bond. So "ene" at the ending instead of "ene" like alkanes. We're still going to number the parent chain, but we're going to make sure to give the first carbon of the double bond the lower number. So it's going to be really the double bond now that has priority, because we want to make sure that the first carbon of the double bond has the lowest possible number. And we're going to have to go over or bridge across both carbons of the double bond. And that's really important, that we must bridge across the double bond. Sometimes that can result in a shorter chain than might overall be present. So again, we have to bridge over both carbons of the double bond. And so sometimes our parent chain is not the absolute longest carbon chain that's present, but it's got to be the longest carbon chain bridging over the double bond in both carbons of the double bond. We're going to follow the rest of the IUPAC rules in that we're going to find in circles any substituents, give them names and numbers, alphabetize them when we are all done. For a cycloalkane, or alkene rather, the double bond has to be numbered so that the 2 carbons have the numbers 1 and 2, and so that any substituents on the double bond have the lowest possible numbers when assigning 1 and 2. So if you've got one substituent, make sure it's on the 1 carbon. So let's go ahead and do some example naming of alkenes. We're going to look for the longest carbon chain that branches or bridges over the double bond. And then we're going to give that double bond the lowest possible number. So let's see, here we've got a carbon chain that is 1, 2, 3, 4, 5, 6 atoms long. So our prefix is hex. We're going to give that hexene ending for that double bond. And then we're going to want to start over here because we want the double bond to have the lowest possible number. And here it starts at carbon 1. And so we're just going to have 1 hexene. And we can't tell if it's cis or trans here because there's 2 hydrogens coming out here and another hydrogen here. It doesn't have the ability to show cis and trans. We would have to have just 1 hydrogen on each side of the double bond to show cis or trans. This is looking similar. 1, 2, 3, 4, 5, 6. So we've got 1 hexene as the root again. But now we're going to have a group on carbon 4. We're going to have a 4-methyl. This example is nice because it illustrates how large the group numbers can really become in order to make sure that the double bond has the lowest possible number. Now let's go over to the next example. 1, 2, 3, 4, 5. That bridges over the double bond. Some folks might try a carbon chain that goes down because it might find a higher number in the chain. 1, 2, 3, 4, 5, 6. So some people might mistakenly call this hex, but unfortunately, this doesn't bridge across the double bond, and so we can't use that highlighted chain of 6, even though it's got more carbons. So let's get rid of that. If we tried this direction going upwards, 1, 2, 3, 4, we'd only have 4. So we really want to stick with 1, 2, 3, 4, 5, or pentene. Now we want to number so the double bond gets the lowest number. So let's start over here. 1, 2, 3, 4, 5. So this is 1 pentene. The double bond is starting at carbon 1 and going on to carbon 2. At carbon 3, we've got a methyl group. And at carbon 2, we've got an ethyl group. We're just going to alphabetize those so that E comes before M. So we'll have 2 ethyl, 3 methyl, 1 pentene. All right, now we have a cycloalkene. So what we've got is cyclopentene. Cyclo for the ring, pent for 5 carbons, ene for the double bond in the ring. Now it's implied with a cycloalkene that that alkene is occurring at carbon 1. So we actually don't have to call this 1-cyclopentene, but we want to number it so that the group has the lowest number. So the 2 carbons of the double bond in the ring have to get the numbers 1 and 2. And here we can have our group be at carbon 3, 3-methyl. Now, we might want to try naming the other way, especially since this is our first cycloalkene. We'll try here. 1, 2, 3, 4, 5. Well, we'd have a 5-methyl if we went with the blue numbering. So we're going to want to avoid the blue numbering. Stick with the red. And stick with our 3-methyl. So we've just got 3-methyl cyclopentene. All right, and in our last example here, we have another cycloalkene. We actually have cyclohexene this time. And again, it's implied that this cycloalkene get the 1, 2. But remember that when we apply the 1 and the 2, we want the group to have the lower number. So it actually gets 1. And then we'll have a 2, 3, 4, 5, 6. It actually gives this group a fairly high number. But we'll have 1, 6 dimethyl cyclohexene. Some students will go, well, if we started up here, 1, 2, and 3, couldn't we name them 2 and 3? It doesn't follow that last rule of when assigning 1 and 2, making sure that your group has the lowest possible number. The other thing that's different about calling it 2,3-dimethyl cyclohexene is it doesn't follow a series of molecules that actually starts with a methyl group right here and calls them 1, 2. And then the methyl group moves around the ring from being 1,2-dimethyl to 1,3-dimethyl to 1,4-dimethyl to 1,5-dimethyl and then to 1,6-dimethyl. And 1,6-dimethyl is like actually the only place where the sum of the numbers is higher than the other option, the 2, 3. So we'll want to stick with that rule of when we're picking the 1 or the 2, making sure that our group has the lowest number 1. And then here we've got this interesting idea of the series going on that we're trying to match when we're naming. So there are two common naming groups that are used pretty frequently, and that's the vinyl group and the allyl group. And so the vinyl group is when you have a two carbon group with a double bond. So this alkene group on some other part of your structure, or an allyl group. The allyl group has three carbons and the double bond is out on the end of the group. My trick to remembering this is simply that to make the V for vinyl, I need two lines to write a V, and the vinyl group is going to have two carbons in it. To make the letter A, I need 1, 2, 3 lines to make an A. 3 lines to make an A, 3 carbons to make a vinyl. Then I just have to remember for the vinyl that that double bond is out on the very end of that chain. So how do I draw vinyl cyclopropane? Well, let's just start with a cyclopropane, prop for 3, cyclo for ring. So it's triangular. And then we want to put a vinyl group on it, so I'm just going to put a group on it, CH, double bonded, CH2. So a 2 carbon group with a double bond. What does allyl cyclopentane look like? I'm going to draw a cyclopentane, and then I'm going to put an allyl group on it. That's a 3 carbon group where the double bond is out on the end of that chain. Now, when it comes to common naming, there are some alkenes, particularly the smallest ones, that are called almost exclusively by their common names. So ethene is often referred to as ethylene, propene is often referred to as propylene, and 2-methylpropene is often referred to as isobutylene. So those are good common names to just have some familiarity with. Now we're going to apply our nomenclature to alkynes. Alkynes are named really similarly to alkenes. You just use the Y and E to show that there's a CC triple bond. Again, you're going to number the parent chain so that the first carbon of the triple bond takes priority. So it's really, again, it's the triple bond having priority. And it's the fact that you're going to have to bridge over the triple bond. So your longest carbon chain has to include both carbons of the triple bond, just like you needed to in alkenes. So just like you need to bridge over the alkene, you need to bridge over the alkyne, including both carbons of it. Just like you need to make the alkene take priority, you need to make the alkyne have priority. And then from there, you just number and name the substituents. So we know we've got to bridge across the triple bond in this example. We're probably going to want to start over here. 1, 2, 3, 4 carbons. And then we just had this 1 methyl group. At carbon 3, there is a 3-methyl. So notice how it might be tempting to start from the left and make this a 1,2-methyl. But it's really the double, or excuse me, here it's a triple bond. It's really the triple bond that needs to take priority, that needs to be at carbons 1 and carbon 2. So then our root is just butene. The triple bond started at carbon 1 and went to carbon 2, and then it's got a 3-methyl on it. So 3-methyl 1-butene. Now let's look for the longest chain on the right here. 1, 2, 3, 4, 5, 6, 7. So we got 7 carbons. 7 carbons is hept. We'll call it heptyne. Let's figure out how to number that. If we start from the left, we're going to have 1, 2, 3, 4 heptyne. Let's try starting from the right. 1, 2, 3. That's going to be preferable. We'd rather have the 3 heptyne. So we'd rather stick with that blue numbering from the right. So we'll want to go with 3 heptyne. And then we're going to have a 6-methyl group. So again, note how large those numbers for those groups can become because what's taking priority is the double or triple bond. In this case, a triple bond. So we'll have 6 methyl 3 heptine. 6 methyl 3 heptine. So now hopefully you have some basic knowledge on how to name some simple alkenes and alkynes, including the cycloalkenes and including some common functional groups like allyl and vinyl.